Okay, continuing with hypothesis testing. Now let us see how we can write confidence intervals on mu, or the mean of the population. This is how it is represented. The P shows that it is a probability of mu existing within this interval. The boundaries of this interval are, the lower boundary is L and the upper one is represented with U, and this one is called as the confidence interval. And this is how we can find it. If we are given the value of alpha, which is as you know is the type 1 error, using this formula we can get the confidence interval, and 1 minus alpha is called as confidence coefficient. Now there are two half widths of this interval. One is the upper half of this interval, which is found by subtracting the value of mu from the upper limit. This one gives us the upper half of the confidence interval, and subtracting the value of lower limit from mu gives us lower half width of the interval of the confidence interval. Now the one-sided lower confidence bound of the one of this interval can be written like this part. This one is the one-sided lower confidence bound, and the probability of this one will be represented like this, that the mu, the value of mean, is equal to or larger than the lower boundary of the confidence interval. It will be found by 1 minus alpha. And similarly we can write one-sided upper confidence bound like this, in which mu is equal to or less than the upper boundary of the confidence interval, and it is represented like this. The probability of mu being less than or equal to the upper boundary of the confidence interval is equal to 1 minus alpha, and alpha once again is the type 1 error. Okay, now confidence intervals on mu when the variance or sigma square of the normal probability distribution is known. So in this condition the variance is known but mean is not known. Okay, so when the mean is unknown but variance is known, then how we can write confidence intervals are like this. So two-sided confidence interval can be expressed like this, that mu exists between x bar is the sample mean minus this is the z statistic, this is the value of z, or the boundary that we can get from the table as you have seen before, and this is sigma, which is standard deviation, and this one we can get from the variance, which is known, because variance is sigma square. We take a square root and we get sigma, which is standard deviation of that population distribution. And the lower confidence bound or the lower confidence interval is x minus this factor, and the upper one is x plus the same factor. So there is no difference, only the difference is the difference of the sign. In the lower one we are subtracting, and in the upper one we are adding them. Okay, and the lower confidence bound can be written like this. Simply it is the left part of this confidence interval, and the upper confidence interval, or also upper confidence bound, can be represented like this. Okay, so this is the left part of the the right part of the confidence interval. So the left part represents the lower confidence bound, and the right part represents upper confidence bound. Let us do an example. In this example, this is the same one that we did during our last session, but now we are approaching it from a different perspective. In this, the response time of a distributed computer system is an important quality characteristic. You know that we are always interested in some characteristics to measure, and which those are called as quality characteristics. So in this thing, in this operation, we are interested in the response time. Our quality characteristic is the response time. The system manager wants to know whether the mean response time of a specific type of command exceeds 75 milliseconds or not. So from the previous experience, he knows that the standard deviation of response time is 8 milliseconds. The standard standard deviation of the response time is 8 milliseconds. This is something he knows from his experience. Okay, and the command is executed 25 times, means our sample size n is equal to 25, and the response time of each trial is recorded. So upon recording, they came to know that the sample average response time is represented with x bar is equal to 79.25 milliseconds. So from the sample they collected, and they took the average, they calculated the average response time in their 25 trials. They found out it to be equal to 79.25 milliseconds. Now you have to find a 95% two-sided confidence interval. Okay, this one is equal to 1 minus alpha, means 100 times 1 minus alpha percent. Okay, so this is something that we need to find out, two-sided confidence interval with 95%. Okay, so if this is 95%, what will be the value of alpha? Actually, alpha will be equal to, if we do not consider it in percentage, if we remove the percentage, it will become 0.95, right? So alpha will be equal to 1 minus 0.95, it will become 0.5, right? So if it is 0.5 and it is two-sided, then we have to divide it into 2. It will become 0.25. Okay, so how does it work then? You will see just now. I will explain it to you during the solution. So in the solution, our sample mean is equal to 79.25 milliseconds. So we can write it like this: our estimation, or the point estimate of this statistic is equal to the point estimate of the parameter mu is equal to 79.25 milliseconds. And since it is two-sided, we are asked to find out the confidence interval means two-sided confidence interval with 95%. Then we can write it like this. From the previous slides, you can see that this is how we write two-sided confidence interval of 100 times 1 minus alpha percent. Okay, so here we observe that it is alpha over 2. So when we found out alpha from here, alpha was equal to 5%, right? So 100% minus 95 is equal to 5%. So half of 5% is 2.5%. If we do not want to write in percentage, then it becomes 0.25, right? So 0.25 on the lower half and 0.25 on the upper half, and this is how we can represent on the standard normal distribution. This is the standard normal distribution. Okay, so Z alpha over 2 on the negative side and Z alpha over 2 on the positive side can be marked like this. Okay, so 2.5% or 0.25 on left side or lower side, and 0.25 on the upper side, right? And means exactly the same way as we did during the during our live class. We can find out the value of Z alpha over 2 from the table. The value will be the same, which was equal to 1 minus 1.96 on the negative side and 1.96 on the upper side or the positive side. Now these are marked on it, and the critical regions are now highlighted as red. So if our value of the z statistic lie any of these regions, in the red regions, we can reject our hypothesis very easily. Okay, this one can be now expressed like this. So the value of z alpha over 2 is 1.96, okay, as we observed from the table previously. Okay, you can go back and see how we did that. The table is already on the Google Classroom, you can check it there. So after calculating this factor and subtracting it from here, we get this one, and on the right side, upper side, we get this one. Now this is one way of expressing it. We can express it another way, like this one, which is more frequently used, or yes, which is most frequently used to express in the measurements. That's 79.25 plus minus 3.136 milliseconds. And how we did that? We subtracted this value, the lower value, or L, from U. You remember, this is the confidence interval, right? So the width of the confidence interval, U minus L divided by 2 will give us plus and minus values of this. Okay, so this one minus this one divided by 2, then we add plus and minus, because 3.136 on left side and 3.136 on the right side. It can go on the left side of 79.25 milliseconds, or towards the right or higher side by 3.13 milliseconds. Okay, now p-value means how we use p-value for hypothesis testing. P-value is the smallest level of significance that would lead to the rejection of null hypothesis. Means that if we find the p-value of a statistic, then we calculate the statistic itself, and if it matches with the p-value or is larger than p-value, we can reject that straight away. So it is a probability that statistic would take on a value that is as extreme as the observed one when mu naught is true. Okay, so if it is equal to or less than that, then we can consider H naught, or the null hypothesis, not to be false. We cannot reject that. Okay, so how we can compute that this p value for our testing? For two-sided tail test, two-tailed test, or two-sided test, which means that when the null hypothesis says that mu is equal to mu naught, means any value of mu, which is means here we are symbolically representing it with mu naught, and alternative hypothesis is mu is not equal to mu naught. It makes it a two-tailed or two-sided test, and for this one we can find the value of p like this. It is equal to 2 times 1 minus, you know that what this is the cumulative standard normal distribution function of this z naught, and you know how we find z naught. Okay, this is the z statistic. And for one tail test, which means that for upper side, or for the upper tail, whenever null hypothesis like this is given like this, then our alternative hypothesis says that mu should be equal to mu should be larger than mu naught, the value which was in the null hypothesis. Okay, so this one makes it the upper tailed test, and it can be, for this one we can find the value of p like this: 1 minus phi of z naught. So you notice that there is the only difference is that there is no two factor multiplication for this. Okay, while for the lower one, where the alternative hypothesis says that the value of mu should be less than mu naught. Okay, for this one the value of p can be calculated just like this. It will be equal to phi of z naught. Okay, so these are the formulas for finding out the p value for two-tailed and one-tailed test conditions. Now let us look at an example of p value. Okay, this is the same example that we did before, but now we are doing it with through p value. So the last time we did was with z statistic. Now we are doing the same problem. We are solving the same problem but with a different approach. Okay, but in this one we are given the value of alpha, which is 0.05. Now this is the value of error, the value of alpha, but its confidence interval will be the same that was given in the previous means on the previous example, that was 95%. So the confidence interval of 95%, alpha will be equal to 0.05. okay, now for this one we can write hypothesis like this, that mu is equal to 75, and alternative hypothesis is mu is larger than 75. So this one makes it an upper tailed test, right? So one-sided upper tail test. So the formula that we will be using can be seen from the previous slide. Okay, from this one, now after this we need to calculate z statistic. The test statistic is this one, the way we calculate z naught. So this is what we get. This one is the sample mean, and this one is the mean of the population divided by the sigma or the standard deviation divided by the square root of the sample size. Okay, so by calculating we get z naught is equal to 2.66. Now we have to find out value of p for this test statistic. Okay, so the value of p, for finding the value of p, the formula that we are going to use is for the one-sided upper tailed test, right? For two-sided we multiply it with 2. Okay, this is for the upper sided one-sided upper tailed test. Now we use the value of z naught here, it is 2.66. Now we have to go back to that standard normal distribution formula and get the value of phi from there. So when we go to table, we find that its value is equal to 0.9961. okay, now we subtract it from 1, we get 0.0039. okay, now this is the value of p. So this one says that the mu or this h naught would be true only for this significance level, okay, for this one only. So if our alpha is larger than this, or the our error, this one which is given as 0.05, if it is larger than this, we are going to reject it. So therefore the mu is equal to 75 would be rejected at any level of significance which is larger than the value of p. Therefore the value or the null hypothesis would be rejected for value 0.01. 0.01 is obviously larger than this, right? But it would not be rejected if alpha or this one is 0.001. okay, so clearly our alpha is 0.05, which is much larger than the value of p. We can very easily reject null hypothesis. Okay, now next is t-test. T-test is for using t-test means it is used under the circumstances when the value of mean is known and the value of variance in the normal distribution is unknown. Okay, so in the previous case our mean was unknown but variance was known, but in this case mean is known and variance is unknown. So in such a case where variance is unknown, we can assume that the variance of the sample is a very good estimate for the variance of the population. Now we can use this formula for calculating a statistic. Okay, this one looks similar to Z statistic, but there is one difference. This is the sample variance. This is the sample standard deviation. Earlier for Z statistic, here we use the population standard deviation of the population, right? So this difference make it a different statistic, and we call it T statistic. And the distribution, the reference distribution that this statistic follows is called as T distributions with n-1 degrees of freedom, and this statistic is called as T statistic. So this one is T statistic, and its distribution is called as T distribution with n-1 degrees of freedom. Here n-1 is n is actually the sample size. If for example the sample size is 20, the degrees of freedom for this T distribution will be 19. Okay, now for a two-tailed test, the hypothesis, this null hypothesis, will be rejected if the value of T statistic is less than or equal to the T alpha over 2. This is similar like we used to write Z alpha over 2. Here it is T alpha over 2, and there is one more factor which is included here, that is the degrees of freedom. So because we have to refer to a distribution that depends on degrees of freedom also, that is why this parameter is important. Okay, now for one-tailed test, the null hypothesis will be rejected for this type, the upper one, where mu1 is to signify that, or to specify that it is related for the alternative hypothesis. So mu1 greater than mu naught, then h naught, or the null hypothesis will be rejected if the T statistic is larger than alpha larger than T alpha n-1. So this one is not alpha over 2, this one is alpha. So for two-sided or two-tailed it is alpha over 2, and for one-sided it is alpha. However, for the situation where the alternative hypothesis says that mu1 is less than mu naught, then h naught or null hypothesis will be rejected if T naught is less than minus T alpha minus n-1. Okay, so the T alpha is the type 1 error that is given, and with the help of this we can find out the significance level, and from that we can go to the tables to find out the values. So just similar to the Z statistic or the table for standard normal distribution, we have a table for T distribution also for different degrees of freedom. Okay, now how we write confidence interval when sigma square is unknown. For this one, two-sided confidence interval on mean can be expressed like this. Very simple. Just replace that Z statistic with this factor and sigma with S. Okay, we get this one. So it is exactly similar to the one that we saw before. So for upper confidence bound, we write it like this, means that this is the one, right? The right side of the confidence interval is the upper confidence bound, while the lower confidence bound is the left side of the confidence interval. Okay, now let us take a look at example of t-test. Here in this example, a rubber can be added to asphalt to reduce the road noise when the material is used as pavement. Okay, the table below shows the stabilized viscosity. Here is the table. So it is a list of stabilized viscosities of 15 specimens. So the sample size is 15 here of the asphalt pavement material. To be suitable for intended pavement application, the mean stabilized viscosity should be equal to 3200. Okay, so the stabilized viscosity should be 3200 in order to in order to achieve what is the goal of this pavement, to reduce the noise. Okay, so this test test this hypothesis. What hypothesis? That the mean value or mu is equal to 3200. Okay, test this hypothesis using alpha is equal to the type 1 error 0.05. Based on the experience, we are willing to initially assume that the stabilized viscosity is normally distributed. So if it is normally distributed, we can use the normal distribution for this. Okay, so here this is the data. Here you are having specimen and you are having the values, but you do not know the value of the variance, right? So if you do not know the value of variance, we can use t-test here. Okay, first, like before, we want to write down hypothesis. So null hypothesis is that mu is equal to 3200, while alternative hypothesis that we propose is it is not equal to 3200. Now we have to compute sample mean first, and sample mean, it can be calculated like this, that sum of all these values, okay, divided by the total number of values. Very simple, we get this one. So sample mean is equal to 3210.73, and the standard deviation, the sample standard deviation can be calculated like this. So this one is equal to the sum of the squares of these values, okay, minus sum of these values and then square of it divided by the total number of values divided by n minus 1. N minus 1 is equal to 15 minus 1, which are the degrees of freedom for t distribution, and we can solve it and get our value of sample standard deviation, which is 117.61. Okay, now let's compute t statistic from this data. So we know that the t statistic is equal to x bar, or sample mean, minus mu naught. Mu naught is the mean of the probability distribution, divided by s, which is sample standard deviation, divided by square root of n, or square root of the sample size. Now we use these values. So 3210 from here and 3200 from here, divided by these s is from here, and n is 15. Okay, so we use these values, we compute it, and we get 0.35. Now we have to find out the critical value, which will help us deciding whether to reject or not reject the null hypothesis. So for critical value, we have to find out the value of t half. Why t alpha half? Because it is two-sided test. When it is not equal to, means that it is two-sided. So we have to find out this value of t. This is alpha divided by 2. Alpha was equal to 0.05, then alpha divided by 2 will be equal to 0.025. 0.025, and this one is n minus 1. N is 15 minus 1 is 14. So these are the degrees of freedom, and this one is t alpha over 2, and from the table of t distribution we can get this value 2.145. This is the critical value. Now so now, since this is our statistic and this is the critical value, and this one is far lower than the critical value, we can simply are unable to reject the t statistic. or sorry, our null hypothesis, because in order to reject null hypothesis, T naught must be larger than this value. Okay, this one should be larger than this if you want to reject it. Okay, you can go back and see for the two-tailed test how it works. So H naught cannot be rejected. We again I will repeat that we cannot write that we accept H naught. In fact, we write that we cannot reject H naught or null hypothesis. Therefore, there is no strong evidence to conclude that mean stabilized viscosity is different from 3200. So in a sense, we accept the null hypothesis that the standardized viscosity is 3200 cp. Okay, that's all. Thank you very much.